Buongiorno a tutti e benvenuti alla seduta di laurea per il corso di laurea magistrale Finance and Insurance. Oggi abbiamo due candidati. Come sapete la discussione avviene in lingua inglese, quindi passo a lingua inglese. So, good morning everyone and welcome to the graduation session for the Master Program in Finance and Insurance. Today we have two candidates. Gian Antonio Davide and Converso Manuel. We start from the latter. So please, Manuel. Okay, so for Manuel Converso, the title of the dissertation is Neural Networks and the Application to Time Series Forecasting. Okay, so I am the, you have to switch on the microphone.
I did that. I turned on the microphone.
Okay. Okay, so I am the supervisor. The second supervisor is Professor Bernardino Algeri. So let me start with a brief presentation of the thesis. So Manuel applied a number of neural network models to forecast the prices and returns of a number of commodities. Okay. So I leave the floor to Manuel for a short presentation. My advice is to focus mainly on the empirical part, okay? Thank you.
Well, today I want to talk about neural networks and their application to time series forecasting. In order to let you understand what I did in the final part of the experiments, I need you to walk you through all of these steps. I will talk about feed-forward neural networks, recurrent neural networks, and then I will introduce the models applied in the experiments. And I will show you the experimental results that I got. Let's get started and talk about feed-forward neural networks. The basic unit of a feed-forward neural network is called a perceptron. A perceptron takes as input the one that we provide the model with, and it calculates the linear transformation. This linear transformation is then passed to an activation function, where this activation function is general and nonlinear type, but it is up to the user to decide which one to use according to the task that it has to perform. This picture shows the case where it is possible to draw a hyperplane such that all the points belong to one cluster on one side of the hyperplane and all the remaining points are on the other side of the hyperplane. Sometimes it is not possible to do that because in this case all the points are correctly classified and we may have more than two classes to account for. So we need more complex structures in order to perform this classification problem. It is an example and it is called a multi-layer perceptron, and in particular this picture shows the input layer, in the layers, and the output layers. The different units are connected to each other through these arrows, and each of these arrows refers to a particular weight. And these weights are what we actually want to learn in order to let the model output to be as close as possible to the actual output. This picture shows the back propagation algorithm introduced by Rumenert in the 1980s. And in particular, starting from the output layer, we have calculated the output at this point. We can compare this output with the actual target, and we can evaluate the loss of the model. In this way, starting from the loss, we can start calculating the gradients with respect to each unit and with respect to each parameter, applying the chain rule of calculus. Once we calculate all the gradients with respect to each parameter, we can apply a gradient-based optimization algorithm. It is an example of the Adam algorithm where I applied this algorithm to minimize a convex quadratic bowl. This algorithm makes use of a first-order moment of the gradient, and this allows to introduce a momentum in the algorithm. It means that as soon as the algorithm goes down along one direction, it gets velocity. At some point, the gradient at a specific point in time suggests to move along a new direction, but it keeps going along the previous direction until the entire velocity is dissipated. Then it starts moving towards the new direction, following a back and forth pattern as the picture shows. When we reach the minimum point, this fluctuating pattern gets less and less serious. And this algorithm also takes into account the second order moment, which is used as a raw measure for the reliability of the first order moment. So the larger the second order moment, the smaller the step taken in the opposite direction of the first order moment. This picture shows then the fitting and overfitting problem, because the ultimate goal of a machine learning algorithm is to learn how to fit the inputs to the output, how to map the inputs to the output. We don't want to reach actually the smallest value possible of the cost function. This picture shows the underlying function, which is given by the blue line, and the model that we're using for fitting this underlying function, which is given by the red line. In particular, it is a polynomial regression model, where the degree of the polynomial is denoted by the letter m. When m is equal to 0 and when m is equal to 1, we have that this model doesn't fit the underlying function very well. But when m is equal to 3, the red line is pretty close to the blue line. When m is equal to 9, instead, we have that the red line goes through all the data points used for training, and in particular, the data points used for training are colored as orange, but it doesn't fit the underlying function at all. So in the first two cases, we are facing the underfitting problem because the model is too simple to learn the underlying structure in the data. But in the last case, we are facing the opposite problem, the overfitting problem. It means that the model has learned the noise in the inputs, but it is not able to generalize well. It is another way to view the same problem. And in particular, at the beginning of when the model capacity is very small, by increasing the model capacity, we can improve the performance of the model both on the training set and the test set. At some point, when we keep increasing the model capacity, the performance on the test set levels off, and then it starts increasing. When the performance on the test set starts increasing, it means that we are overfitting because the model is not able to generalize. One way to overcome this issue, the overfitting problem, is by increasing the number of training examples. For example, in this picture, I'm showing the performance of the n-degree polynomial when I increase the number of examples. When n is equal to 100, we have that the red line is very close to the blue line. Let's talk about recurrent neural networks, which are the ones that I used in the experiments. It is the basic unit of this model, and in particular, this unit takes as input the one that we provide the model with, and in this picture are denoted as xt, and the previous hidden units, which are denoted as ht-1. These two inputs are then combined together, and the final transformation of these inputs is passed to an hyperbolic tangent activation function, which takes values ranging from -1 to 1. This output has been denoted in the picture as ht, and it will be used at the current time step to produce the output yt, and at the next time step to perform further calculations. These different units can be stacked one next to the other, and it is like a repetitive application of a feed-forward neural network, where the different feed-forward neural networks are connected one to the other to hidden connections. And in particular, these models share parameters at 2 times, which means that the input weight, for example, at time 1, it's the same as the input weight at time t. This is particularly important because whenever the model is able to recognize a particular sequence, it means that it has learned the particular features in the sequence. It recognizes these features whenever they happen. They can occur at the beginning of the sequence or at the end, it doesn't matter. During the forward pass, we can calculate the different activations and the different outputs, and we can evaluate the losses. They are stored until the back propagation, the backward pass, where the gradients are calculated. In particular, in this phase, the algorithm is called the back propagation algorithm, but this is nothing different from the back propagation algorithm we saw when talking about feed-forward neural networks, but it's just applied to simple recurrent neural networks. In this case, since the parameters are shared, we need to be careful though, because we need to evaluate the contribution of each parameter to the loss at each time step, and then we need to sum overall these contributions. Once we have the gradients, we can apply gradient-based algorithm to minimize the cost function. The long short-term memory models are more complex because they have getting structure in them. So in this case, we have three gates units, and in particular, they are the forget gate, which establishes how much the previous information is still important to be brought forward, and the input gate, which establishes how much of the information learned from the current inputs is important to be stored in the internal memory. So the new information and the previous information are then combined together to form an updated version of the internal state, which will be passed to the parabolic tangent activation function and multiplied by the output gate. The output gate establishes how much of the current memory content is important to produce the output at time t. We can stack these different units next to each other, one next to each other, and in this way we got the enrolled version of the LSTM model. During the forward pass, we evaluate the different activations and the different losses. We store these values until the backward pass. In this case, the backward pass is a little bit different because the error is allowed to go backward only to the internal state S. But whenever the error tries to leak out the different gate units, the error is truncated to 0. Why is that? Duper suggests this kind of procedure because in this way it is possible to prevent the overflow from vanishing. And the vanishing overflow is particularly problematic with simple recurrent neural networks because they didn't allow the network to learn long-term dependencies. Let's discuss now the models used in the experiments. In particular, I'm going to describe the variables that I used for predicting the futures prices, in particular the futures log returns written on commodities. And the variables are the standard poor 500, which is a market capitalization weighted index reflecting the 500 companies with the largest capitalization, the Baltic Exchange Rate Index, which is a benchmark price for shipping raw materials by sea, the SIBO Volatility Index, which is a looking forward risk measure calculated on the options written on the standard poor 500 and listed by the Chicago Board Options Exchange. I used the indicator for the emerging markets, the DIX Index, which is a geometric weighted average of the US exchange rate against other currencies used by the major trading partners of the US, in particular, for example, the euro or the Japanese yen, the TED spread, which is the difference between the LIBOR rate and the risk-free interest rate in the US. Then I used the risk-free interest rate on the 3 months government debt, the federal funds rates, and the yield calculated on corporate bond issued by corporations rated as BAA and AAA by Moody's, the crude oil price, and the open interest, where the open interest is the number of contracts not settled yet. I mean, futures contracts. In this case, it's written on the commodities that I'm going to describe later. Then I used the implied volatility and the historical volatility calculated over the past 20 and 10 days. In particular, this picture shows instead the explained variables. I reported the ticker and the corresponding description. Long story short, all these commodities can be distinguished into 3 broad categories. So I used agricultural products, metals, and energy products. Once I've been given the dataset, I decided the dimension of the training set and the auto sample. The auto sample has been used for testing. Instead, the training set has been used for training the different models. The rolling window method consists in rolling these windows by keeping the dimension fixed. And in this way, I ended up with a number of training sets and a number of auto-assembled sets. The auto-assembled sets have a dimension equal to 5, which means that I wanted to evaluate the different models' ability to make 1 step ahead forecast up to 5 steps ahead forecasts. And since I ended up with different training sets, it means that I end up with a given number of 1 step ahead forecasts, 2 steps ahead forecasts, and so on. And this will be used later on to produce the measure to evaluate the model's ability to forecast. Then I applied the Denmax model. The Denmax model is an ARMA model with the addition of exogenous variable. There's a problem though in this case, because if we want to forecast yt plus 1, which is the explained variable, we need to know the expected value of the exogenous variables as well at time t plus 1. Since the runtime would have been too much longer, I preferred not to estimate a particular model to forecast these variables as well, but I used as expected value the actual variable at that time step. Of course, in practice, it is not possible to do that, so we needed to estimate more models. And then when training these models using the training sets derived by the roll window method, I determined the dimension of these models using the BAC information criterion. It is the outermost structure that I applied for training the simple recurrent neural network and LSTM. I wanted to simulate what we do with the ARMA model, and in particular, the target at the previous time step is fed back into the model at the next time step, along with the exogenous variables. And at each time step, the output is calculated and it's compared to the actual target. Then I used the early stopping criterion, which means that as soon as the error started increasing on the validation set, I stopped the training. And the number of video units I used for both models have been set equal to 32, and the inputs have been standardized before providing them to the model. It is the formula that I applied for calculating the performances of the different models. So for each training set, I have I calculated the forecasts, and I have a number of these forecasts thanks to the rolling window method, referring to a specific time step. So then I compared the different forecasts with the actual target. I squared these forecasting errors, and they averaged them all, being careful not to confuse the different forecasting horizons. Then I took the square root. So in the end, I ended up with a root mean squared error for each forecasting horizon for each model. The results have been summarized in this picture. Each of this bunch of bars refers to a particular time horizon. In particular, the time horizon goes from 1 to 5. And the color refers to a particular model. The orange bar refers to the LSTM model. The green bar refers to the recurrent neural network model. And the red bar refers to the adjusted Denmax model. I removed the insignificant variables in this model. And the purple bar refers to the Denmax model without any adjustment. Then I compared the performance of the adjusted Denmax model to the performance of the Denmax model without an adjustment, and I noticed that most of the time the adjusted Denmax model performs a little bit better than the Denmax model, but the improvement is not very huge. And when I compared the performance of the LSTM model and the recurrent neural network model, I noticed that the best performing model was the LSTM model. In the end, I compared the performance of the LSTM model with the Denmax model, and I noticed that the best performing one was the Denmax model. But the runtime for training these models was much longer when for the LSTM model than for the Denmax model. But I think that there is advantage in using the LSTM model, though, because we can increase the number of outputs at each time step. So we can not only forecast the value for y, but also the values for the exogenous variables, and we can, in principle, use only one model to perform the tasks. Instead, if we wanted to use the Denmax model, we had to use an Denmax model for estimating the variable y, but many other models for estimating the exogenous variables as well. Thank you a lot.
Okay, thank you very much. Any questions?
Yes, I would like to make you a question, please.
Yeah, go back there, please.
Actually, I would like to ask you how long time does it take to estimate this machine learning model, and then
for performing the task, the machine learning models took 3 days. Instead, the Denmax model took just 1 day.
Okay. Then, do you think that this model presents some limitation compared to other classical model like Denmax?
Yeah, I think that the Denmax model performed better, and the task was much less complex in the sense that we needed to estimate to consider less hyperparameters instead with the Denmax with the LSTM model and the simple RNN model. We had to consider different hyperparameters starting from the optimization algorithms, for example. And it would have required, for example, using cross-validation. But since the models I had to estimate to perform the task was very huge, I didn't do that. I selected the number of hidden units, for example, equal to 32. But the performance would have improved if I had the possibility to use cross-validation, for example. And in the end, since I didn't bother about these problems with the Denmax model, I said that if we have to forecast daily data, I prefer using the Denmax model than the LSTM model. But the other advantage that I found is that since the Denmax model has only one output at a time, instead the LSTM model or the recurrent neural network models in general give us the possibility to extend the number of outputs. In this way, we have the chance to reduce the overall runtime of the model, because to forecast y, I need only one model instead of many models as I should do with the Denmax models.
Okay, and just to finish, among your exogenous variable, which one is the most important to input into the model?
Okay, it depends on the variables that we are estimating. For example, if you use the energy products, the most important variable was the crude oil, for example, and it's quite reasonable because the crude oil, the source of the energy, the basic source of the energy is the crude oil.
What about VIX index?
VIX index?
Yeah.
Okay, the VIX index, because all these variables have been, the basic unit of all these variables is the US dollar. So I think that the US dollar is capable of, the value, how changes the value of the US dollar is capable of affecting the price of the different commodities.
Okay, for me it's okay. Thank you.
Okay, thank you. Just one suggestion before you go. I think something you didn't try, but you may try at a later stage if you want to improve your knowledge about these models. Something that is quite useful in this context is to combine forecasts. You didn't try that, did you?
No.
Okay, so you can one possibility based on the root mean square error, for instance, or other metrics, you can put together forecasts from different models. There is a huge literature on that, how to combine forecasts. So it's something maybe worth worth considering if you decide to study this topic a little more. Okay, thank you. Right, next we have Davide Di Gianantonio, please. The title of the thesis is Extreme Value Theory and Solvency Requirement Computation for Non-Life Insurance. The first supervisor is Professor Steiner, so I ask Professor Steiner to briefly introduce the candidates. Thank you.
Yes, thank you. Davide Di Giannantonio has studied in his thesis the extreme value theory, and he was able to apply it to the problem about the solvency required computation. Then he was able to apply this technique to a data set taken from R, package of R, and then he computed some solvency requirement by applying condition about risk or tail about risk and other risk measures. So, David, I can start this presentation.
Okay, the purpose of this thesis was to study and analyze the statistical approach of the extreme value theory to model, as the name suggests, extreme events in the non-life insurance field and derive computation about capital requirements for a non-life insurance company. In this presentation, we will provide a definition of the extreme value theory and its two main approaches, a definition for the measures of risk useful for determining the capital requirements, and then we will see a real data application. Extreme events could be defined as low frequency and high severity events. They are located in the tail of the distribution, and the classical statistical approaches are not able to, cannot adequately explain them. So the extreme value theory instead focuses on the tail of the distribution, and its main characteristic is to explain the behavior of large values, even when these values are not many. In extreme value theory, two are the prevailing approaches that could be followed, the block maxima and the peaks over threshold. The block maxima consists in dividing the observation period into non-overlapping period of the same length and then keeping only the maximum observation over each period. Instead, the peaks over threshold approach consists in identifying a sufficiently high threshold and then selecting all the observations which exceed such threshold. In financial and insurance application, the preferred approach is the second one because it allows to consider all the relevant observations without missing no one. And the Pickens-Balkenende theorem suggests that the conditional distribution of the losses, given that these losses exceed a high threshold U, are well approximated by the generalized Pareto distribution, which in this slide is presented in the two parameters form, where C is the shape parameter and tau is the tail index, is the scale parameter. The modeling of extreme events is fundamental also to determine capital requirements for an insurance company, and in this context, risk measures are very useful in determining this requirement because it suggests the amount of capital an insurance company has to set aside to protect itself and the policyholder. The risk measures on which we have followed are the value at risk, which is the maximum losses not exceeded with a given high probability, and the tail value at risk, which is instead the expected loss over a given time horizon once that the value at risk at the chosen confidence level has been exceeded. For what concerns the application, the peaks over threshold approach was used to model a dataset contained in the RStudio software CAS datasets, in the RStudio library CAS datasets, consisting of more than 2,000 large fire insurance claims in Denmark between 1980 and 1990, and the computation were made using the RStudio software. In this slide, on the left, we could observe the time series of the data, and some huge losses is already observable, while on the right, we find the histogram of the log claim size, which is strongly skewed to the right due to the fact that the mean of this observation was larger than the median. Now, to verify whether the data set is suitable to be modeled by a generalized Pareto distribution, we need first to apply graphical inspection, because in order to be modeled by a GPD, the underlying distribution must be EV-tailed. On the left, the empirical distribution function presented a decreasing linear trend, which is an indication of EV-tailedness, while on the right, the QQ plot against the exponential distribution presented a concave shape, which is also an indication of EV-tailedness. So consequently, we could confirm that the large fair insurance claims can be fitted by a generalized Pareto distribution. The next step consists in the choice of the threshold, and this choice is fundamental because if the threshold is set too low, we are no more considering only extreme values, while if the threshold is set too high, we have few observations to carry out the analysis. So the choice of the threshold was made using the mean excess function, here presented by the mean excess plot, and the parameter stability plots. Both suggested that the threshold was something in between 5 and 15. For this reason, the threshold selected were 10 because it seems to be the most reasonable one, and 15 because we would like to see if there are more differences or similarities in choosing a different threshold but belonging to the same reasonable range. Applying the model using the GPD function of the Evir package of R, we can observe that the fit was very satisfactory for considering both the threshold. On the left, the threshold 10, and on the right, the threshold 15. We can see that the fit was very satisfactory due to the fact that the two curves corresponded. Moreover, looking at the table in which we have also provided the threshold value 5, we can observe that despite the difference in the number of excesses, the value of the shape parameter does not vary significantly, and also the standard error keeps fairly low value. These are indication that the range chosen for the threshold was appropriate, and the generalized Pareto distribution well estimated the details of the loss severity distribution. The modeling of extreme claims is fundamental to derive conclusions about the capital requirements of an insurance company, because sometimes these extreme losses could be so severe as to require an extra capital to its coverage. In this context, the peaks over threshold approach provides a useful statistical model for the computation of extreme risk measures such as the value at risk and the tail value at risk. In this slide, I've presented a comparison between the value at risk coming from the GPD approximation with their empirical counterparts, and the values are expressed in millions of Danish krone. We can observe that the more we increase the probability level, so the more we go deep in the tail, the more the difference between the risk measures coming from the GPD approximation and their empirical counterparts increases. And this was the result expected, since the empirical risk measure does not come from an approach which accounts for the tail behavior of the distribution. But since the observation of our dataset were almost daily, so it tells us only the capital to be set aside in order to face the next losses. So they were based on the next occurrences. So to extend the analysis, we have considered also a monthly time horizon in order to get an amount of capital which is needed for the loss coverage of the incoming month. So first we have collected the observation monthly, and then we have simulated 100,000 possible number of occurrences over the next month using a Poisson and a negative binomial distribution. And in particular, we observed that applying a chi-square test statistic, that the negative binomial distribution better fitted the observation. Then, with each of the fitted distribution for the monthly claim number and the distribution for the claim size, we have built a function which simulates random monthly losses. In particular, since the number of occurrences were 100,000 coming from the Poisson or the negative binomial distribution, we have generated the random monthly 100,000 monthly losses for the next month, and again computed the value at risk and the tail value at risk with a monthly time horizon. we can observe that the risk measures coming, both the value at risk and the tail value at risk coming from the negative binomial distribution suggested an amount of capital a bit higher with respect to the ones coming from the Poisson distribution. In conclusion, what we can say about this analysis on the risk measures based on the capital requirements, we can say that if the risk measure comes from an approach which does not consider the tail behavior of the distribution, they tend to underestimate the potential loss that could arise, especially in presence of extreme events. That in this case, extreme events are represented by large claims. Moreover, we can confirm the statement that choosing the value at risk as a benchmark for solvency capital requirement could be also dangerous for an insurance company because, as we know, the value at risk only suggests the maximum loss for a given probability level, but when this probability level is exceeded, it does not suggest anything. So it could be a risk measure not appropriate when dealing with extreme losses such as those analyzed. And for this reason, we have also provided the tail value at risk, a measure that is gaining a credibility of the insurance industry. And mathematically speaking, it has better properties with respect to VAR since it is a sub-additive risk measures. And moreover, thanks to the GPD approximation, the accuracy of this risk measure could be improved, and consequently, we could have derived more reliable capital requirements. Thank you for your attention.
Thank you. I have a couple of questions. One is about one particular table with the estimate for the XC parameter. Maybe if you can go back. So the standard errors increase with U. Can you explain that? Do you think it makes sense? Can you give an explanation for that? Yeah, this one.
This one?
Yeah. Why do the standard errors increase with the threshold?
And the standard error increased, increasing the number of threshold because increasing the number of increasing the threshold, the number of excesses decreases, so there are less observation to carry out the analysis, so it is a bit uncertain for.
Yeah, exactly. So it is something that one expects. I mean, if you increase the threshold, you decrease the number of observations, you base the estimation on, therefore, the uncertainty increase. Next, I have another, well, not really a question, more like a suggestion, something you can study in this context. Now, you do not report the formula for tail VAR expected shortfall, but you have it in the thesis.
Yeah.
One of the components of the formula is the probability of exceeding the threshold, isn't it?
Mm-hmm. Yes.
Yeah, okay. So something else you can do in this context is to make this probability time varying. So you can give some dynamics to this probability. You can also make, there are ways to make the XC parameter dynamic as well. Mm-hmm. So if you make the probability of exceeding the threshold dynamic, like in a Garch type of model, mm-hmm. You can use, for instance, a model called CAR, conditional autoregressive logistic, because you make the logistic transformation of the probability to be to depend on its lag value and some and the data. Mm-hmm. Okay, so if you combine the two, you get the so-called CAR-POT model. Okay, I have a paper on that with her actually. We recently published something on that. So they typically perform better than these static models. Okay, so just a suggestion, maybe something you can look up. Yeah. Any additional questions? No. Okay, so we stop here. Thank you very much.
Thank you.
The panel will now reconvene. We will discuss the. Sì, ok, ci spostiamo di là per discutere i voti finali dei due candidati. Grazie.